chance does things well. This phrase, even if it seems trivial, actually hides one of the most important questions humanity has ever asked, because in fact, by uttering these words, you have just done something extraordinary. You have essentially personified chance, turning it into a kind of entity, a conscious force that does things. As if somewhere in the universe there existed a kind of invisible conductor called chance, kindly arranging your small affairs. But wait, think for a moment about what you just said. Chance does things? So chance would have a will, an intention, a plan? How can something fundamentally random do anything at all? This apparent contradiction leads us to the heart of a mystery that has obsessed the greatest minds in history. What exactly is chance? Does it really exist? Or is it just a name we give to what we don't know? And if it exists, what is its deep nature? These questions are not just a simple intellectual game for philosophers lacking inspiration. They touch the very heart of our existence, the deep nature of reality. Because you see, if chance truly exists, then the universe contains an irreducible part of unpredictability. The future is not predetermined. Your next thought, your next decision, your next encounter is not determined by an immutable cosmic plan set since the Big Bang. But if chance does not exist, you are merely a sophisticated automaton executing a program written 13.8 billion years ago. Every beat of your heart, every synapse firing in your brain, every word you speak tomorrow was already inscribed in the equations of the universe. Being born, you discover your life, but you do not create it. Between these two worldviews lies an immense philosophical abyss. On one side, a creative, unpredictable universe where the future remains to be written. On the other side, a deterministic cosmic machine where everything is predetermined from the beginning of time. For centuries, this question remained in the realm of pure philosophy. But in the 20th century, something extraordinary happened. Science found a way to settle this debate. Age-old, the answer it discovered is perhaps stranger, more troubling, and more beautiful than philosophy could have imagined. But first, let's start by demystifying what we call chance in our daily lives. Because what we will discover is that most of the time, we are mistaken. What we take for chance is often just a disguised thing. You flip a coin, heads or tails. One might think it's chance, but let's look at what really happens, frame by frame, as if we had an ultra-fast camera capable of filming the invisible. At the precise moment your thumb propels the coin, it acquires an angular velocity. This speed is determined by the exact force you applied and the precise angle of your motion. Imagine your thumb as a medieval catapult launcher. The projectile's trajectory depends entirely on the tension of the rope and the angle of launch. Nothing very mysterious about that. The coin then follows a perfectly calculable trajectory according to Newton's laws. Gravity pulls it downward with a constant acceleration of 9.86 meters per second squared. Air resistance slows its rotation according to the equations of fluid mechanics that any engineer can solve. When it falls back into your palm, the number of rotations it has performed determines absolutely certainly whether it will show heads or tails. Physicists have proven this in a spectacular way. They built machines capable of flipping a coin and predicting the outcome every time with 100% accuracy. The randomness of the coin was just an illusion born from our inability to measure and calculate all the variables of the game. So why do you talk about chance? Because you don't know these variables. Chance here is your ignorance. Disguised as a cosmic mystery, it's like watching a magician make a rabbit appear and attributing the trick to supernatural forces, when it's simply a technique you don't know. This view of chance as ignorance was formalized by the mathematician Pierre-Simon Laplace. In 1814, Laplace, a fascinating man and a genius, contributed to almost every field of mathematics and physics of his time. He imagined an intelligence, famously known as Laplace's demon, that would know the position and velocity of every particle in the universe. Here is what Laplace wrote in his philosophical essay on probability. We must regard the present state of the universe as the effect of its past state and as the cause of the one that will follow. For Laplace, the universe was a gigantic deterministic machine. Each event was the inevitable consequence of previous events, going back to the initial conditions of the Big Bang. Chance didn't really exist. It was only the name we gave to our inability to calculate systems too complex for our limited means. Imagine the universe as a game of cosmic bowling. At the moment of the Big Bang, Someone gave the kickoff, and since then the balls roll and collide. They bounce according to perfectly predictable laws. If you knew the position and velocity of each ball at a given moment, you could calculate where they will be in 1,000,000 years. Your meeting tomorrow with an old friend already written in the equations. Your next creative inspiration already determined by the state of your neurons. This view was reassuring, elegant logic. The universe was predictable, orderly, and rational. You just needed enough information and enough computing power to predict anything. It was the time when, during Calvin, one of the greatest physicists of his time, confidently declared that there was nothing left to discover in physics, except perhaps to refine a few details in the 6th decimal place. But even within the framework of classical physics, cracks began to appear in this perfect deterministic vision. Henri Poincaré, at the end of the 19th century, discovered that some deterministic systems could have chaotic behavior of variation. Infinitesimal and poorly measured initial conditions could lead to completely different results. This is what we call today the butterfly effect, a metaphor that hides a mathematical reality. Strictly speaking, the flap of a butterfly's wings in Brazil can theoretically trigger a tornado in Texas, not by magic but by progressive amplification of perturbations. Through a complex system, imagine trying to balance a pencil on its tip. Theoretically, it's possible. The laws of physics do not forbid it. But in practice, the slightest vibration, the tiniest draft of air, the smallest imperfection on the surface can make the pencil fall. And depending on the exact angle of that microscopic perturbation, the pencil will fall to the right or to the left. A perfectly deterministic but practically unpredictable system. Weather is a perfect example. We know the equations that govern the atmosphere. They are the same Newton's laws that govern the motion of planets, and yet we cannot predict the weather in 3 weeks. Why? Because the atmosphere is a chaotic system where small causes produce large effects. And be careful, chaos is not randomness. It's practical unpredictability in a deterministic system. The system always follows precise laws, even if we cannot precisely predict its behavior. It's like a book written in a language we cannot read. The text exists, it has meaning. It's just that we cannot decipher it. Today, this illusion of chance has taken new forms, more sophisticated and more troubling. When Netflix recommends a movie you love, when Google anticipates your search even before you finish typing, when your smartphone predicts your morning commute. We are talking about artificial intelligence and predictive algorithms. These systems only push to the extreme the logic of Laplace's demon, collecting as much data as possible on your past behavior to predict your future actions. And it works with a sometimes disturbing precision. Amazon often knows what we want to buy even before we know it ourselves. Trading algorithms buy and sell stocks in milliseconds, anticipating market movements. Algorithms have become modern versions of Laplace's demon. They don't know the position of every particle in the universe, but they know your habits, your preferences, your behavioral patterns. And with this information, they can predict your future choices with troubling precision. Are we so predictable, or are these algorithms simply revealing that what we took for chance was in fact nothing but complexity, disguised that our decisions, our tastes, our desires follow hidden patterns that we do not perceive, but that a machine can detect? Until now, everything we have called chance has turned out to be something else. Ignorance, complexity, deterministic chaos. Chance seems to be only a convenient way to name our inability to predict systems too complex for us. But here is the question at the heart of this video. Does there exist a true randomness? A randomness that is not due to our lack of information, but that is inscribed in the very nature of things? A randomness that even Laplace's demon with perfect knowledge could not eliminate? To answer this question, we must leave the familiar world of coins and predictive algorithms. We must dive into the universe of the infinitely small, where the rules of the game change completely, because it is there, in the quantum world, that science has discovered something extraordinary. The randomness that cannot be eliminated even with perfect knowledge. The randomness that seems to be a fundamental property of the universe. The story begins in the 19th century, in a dusty laboratory, where physicists are trying to unravel the secrets of the atom. They expect to discover a miniature world operating according to the same rules as our macroscopic world. They are going to discover something more disconcerting. Imagine yourself in the shoes of these scientists. You have just discovered the existence of atoms, these elementary bricks that make up everything around you. You tell yourself, okay, perfect. Now all you need to do is apply Newton's laws to these little marbles to understand everything. You don't yet know that you are about to open physics' Pandora's box in 1896. Henri Becquerel. He accidentally discovers radioactivity and places uranium salts on a photographic plate wrapped in black paper. When he develops the plate, he discovers that it has been exposed. Uranium spontaneously emitted an invisible radiation capable of penetrating matter. But here is what will disturb physicists for decades. Take a radioactive atom, say an atom of uranium-238. This atom will decay and transform into thorium-234. We know it's going to happen. We even know the probability with remarkable precision. Half of the uranium-238 atoms decay in 4.47 billion years. But that's where it becomes a mystery. We cannot predict when a particular atom will decay. Not because we lack information, but because there is apparently nothing to predict. The atom may decay in the next second or in a billion years. There is no signal announcing the decay, no internal clock counting down. There is no hidden variable that determines the fateful moment. It's as if this atom were flipping an invisible coin at every instant and would decay when it gets heads. But this coin does not follow Newton's laws. It seems to obey completely different rules, rules that defy our most basic logic. In 1905, Albert Einstein adds another piece to the puzzle. By explaining the photoelectric effect, when a metal plate is illuminated with light, electrons are ejected. But here's what's strange. The energy of the ejected electrons does not depend on the intensity of the light, but only on its color. Einstein proposes a revolutionary explanation. Light is not a continuous wave, but consists of small packets of energy called photons. Each photon carries a precise energy determined by the frequency of the light. When a photon hits an electron, it transfers all its energy at once, like a billiard ball striking another ball. This discovery, by the way, earned him the Nobel Prize in 1921, but it raises a more interesting question. If light is made of particles, how to explain interference and diffraction phenomena that clearly point to light being a wave? To understand how much the quantum world defies our intuition, let me describe the experiment that changed everything. Richard Feynman, one of the greatest physicists of the 20th century, said that one experiment so strange contained all the mysteries of quantum mechanics. Imagine a wall with two parallel slits, and behind this wall, a screen capable of detecting particle impacts. You send electrons one by one towards the slits, as if you were firing microscopic ping-pong balls at the two openings in the wall. If electrons were really classical particles, you would expect to see two bands on the screen corresponding to the electrons that pass through. Through each slit, some electrons would go through the left slit and others through the right slit. There would be two separate piles on the right and left of the screen. But that's not at all what happens. Instead of two bands, you get an interference pattern. Alternating bands of high and low intensity, exactly as if the electrons were waves passing through both slits simultaneously and interfering with each other. But here's where things get really puzzling. If you place a detector near one of the slits to see which one the electron goes through, the interference pattern immediately disappears. The electron then behaves like a normal particle and only goes through a single slit. The act of observing changes the behavior of the electron. When no one is looking, it goes through both slits. When observed, it chooses one slit. But how does the electron know it's being observed? How can information about the detector's presence influence its behavior? And above all, what exactly happens at the moment of measurement? In 1927, Heisenberg formulated what would become one of the most famous and most misunderstood principles of physics. The uncertainty principle states that one cannot simultaneously measure certain pairs of a particle's properties with precision. The principle is expressed by a mathematical inequality, simple but quite profound. Basically, the more precisely you measure the position of an electron, the less precisely you can know its speed, and vice versa. This limitation is not due to an imperfection in our instruments, but to the very nature of quantum reality. For a long time, physicists thought this uncertainty came from the fact that to measure the position of an electron, you have to shine a photon on it, and that photon inevitably disturbs the electron. The uncertainty seemed to come from this unavoidable disturbance, but the experiments we are going to explore have shown that this uncertainty was insufficient. The problem is deeper than a simple measurement disturbance. It is not that we are uncertain about the properties of particles. It is that the properties do not exist in a defined way before measurement. Moreover, we should no longer speak of the uncertainty principle, but rather the indeterminacy principle, and this nuance changes the whole of quantum mechanics. It shows us a vision of the world that defies our logical senses. Before measurement, the electron was not really in a defined state. It exists in what is called a superposition of states. It simultaneously passed through the left slit and the right slit. It is in a state that has no equivalent in our macroscopic world in quantum mechanics. The state of a particle is described by what is called a wave function, denoted psi. This mathematical function encodes all probabilities. The probability of finding the particle here or there, with such and such speed, and in such and such state. Before measurement, the function can thus be a complex superposition of multiple states, and the particle is everywhere at once according to the probabilities defined by this function. It is as if you had quantum dice simultaneously showing all their faces, each with a different probability. But at the moment of measurement, something remarkable occurs. The wave function collapses. All possibilities disappear except one, which becomes reality. And the choice of this particular possibility is purely random, determined solely by the probability encoded in the wave function. It is as if the universe flips a coin with every measurement, and the result of that flip determines which possibility will be realized. But unlike our classical coin, this flip is not determined by hidden initial conditions. It is fundamentally random. This interpretation of quantum mechanics sparked one of the most passionate debates in the history of science. On one side, Albert Einstein, the father of relativity, refused to accept that the universe is fundamentally random. On the other, Niels Bohr, of the Copenhagen school, maintained that quantum randomness was real and irreducible. Einstein could not accept that the universe was governed by chance. God does not play dice, he said, but for him, quantum mechanics was incomplete. There must exist hidden variables, secret properties of particles that we do not yet know, which would determine their behavior. According to Einstein, particles had well-defined probabilities before measurement, like hidden cards in a deck. If we know these secret cards, we could predict the outcome of every measurement. Randomness was only a manifestation of our ignorance. Bohr, on the contrary, argued that quantum randomness was real and irreducible. For him, the properties of particles did not exist before measurement. Reality was fundamentally probabilistic. Particles had no hidden cards. They were in a superposition state until the moment of measurement. In 1964, an Irish physicist working at CERN would revolutionize our understanding of reality. John Bell was not seeking glory. He simply wanted to understand whether Einstein was right. What he would discover would shake the foundations of physics. It will force us to accept that the universe is even stranger than we imagine. Bell's genius was to transform a purely philosophical question into a precise mathematical test. The debate between Einstein and Bohr seemed insoluble. If particles have hidden properties, or if they are truly in an indeterminate state, Bell will find a brilliant way to answer this question. His reasoning is dazzlingly simple. If Einstein is right and particles have predetermined properties, then certain measured correlations between entangled particles must respect precise mathematical limits. If these limits are violated, then Einstein is wrong and Bohr is right. To understand Bell's reasoning, we must first grasp what quantum entanglement is. Imagine two particles created together. These photons are entangled in a process that conserves certain properties. For example, two photons emitted simultaneously by an excited atom. Their properties remain correlated even when separated by large distances. If you measure the polarization of the first photon and find it is vertically polarized, you instantly know that its entangled partner, even if it is at the other end of the galaxy, will be horizontally polarized. This correlation is perfect and instantaneous. Einstein called this spooky action at a distance, and he refused to believe it. For him, this correlation was simply explained. The two photons had predetermined polarizations from their creation. Like two cards drawn from a deck, if one is red, the other is necessarily black, and Bell will imagine an experiment to test this hypothesis. Take two entangled photons. send them to two distant detectors, and each detector can measure polarization along a certain orientation. Under different angles, the experimenter can choose the measurement angle at the last moment. When the photons are in flight, if Einstein is right and their polarizations are predetermined, then the correlations between measurements must respect mathematical constraints. Bell calculated these constraints and expressed them as an inequality. The most famous inequality is written like this. That may seem abstract, but it encodes something deeper. If particles have predetermined properties, then this expression can never exceed 2. It is an absolute limit imposed by logic and local realism, but quantum mechanics predicts that this limit can be violated in certain configurations. Quantum theory predicts a maximum value of about 2.83. This difference between 2 and 2.83 may seem small, but it hides a gigantic philosophical stake. If the equations give a value greater than 2, it means Einstein was wrong. Particles do not have predetermined properties, and they are truly in an indeterminate state before measurement. Even more disturbing, this means that locality, the idea that an object can be influenced by its immediate environment, is violated. In 1982, Alain Aspect performed the experiment that settled the debate, and the results are definitive. The measured correlations clearly violate Bell's inequalities. Instead of a classical limit of 2, Alain measured values close to 2.7, which is exactly what quantum mechanics predicts. Einstein was wrong. Particles do not have predetermined properties. They are truly in indeterminate states before measurement, and when they decide at the last moment of measurement, they do so purely randomly. Even more disconcerting, the entangled particles seem connected at a distance. When you measure the polarization of a photon in Paris, its entangled twin instantly knows the result and adjusts its polarization accordingly. When two particles are entangled, they form a single quantum system, even if separated by light years. Moreover, there is a great misunderstanding about entangled particles. Many think they are two particles exchanging information instantaneously, which would amount to communicating faster than the speed of light, which is technically impossible. When two particles are entangled, you must understand that they form only one quantum system, even if they are separated by light years. It's not really that they communicate, it's that they are no longer truly separate. They constitute one and the same quantum object extended in space. When you measure an entangled particle, you get a random result, but that result instantly determines the state of its partner, even if it is at the other end of the universe. And if you wonder how this information can travel faster than light, the answer is that no information travels. Entangled particles do not send messages. They are simply two aspects of the same quantum reality. It's as if you had one quantum coin that you could cut in two. Each half, even separated by galaxies, would remain connected to the other. When one half decides to show tails, the other automatically shows heads, not because it received a signal, but because in fact it's the same coin. In any case, experiencing this aspect forces us to accept a disconcerting reality. The universe contains an irreducible randomness, a randomness that cannot be eliminated by more information because there is no hidden information. And this quantum indeterminacy has an extremely important consequence. It means that the future does not yet exist. It is not written somewhere in the equations of the universe waiting to be discovered. It is created as it goes, quantum event by quantum event. Each time a radioactive particle decays, the universe randomly chooses the moment of that decay. Each time a photon crosses a semi-transparent mirror, the universe decides whether it will pass through or be reflected. Its choices are determined by nothing other than pure chance. Paradoxically, this randomness that seems to introduce chaos into the universe is also a driver of creativity and complexity. In a purely deterministic universe, everything would be predictable. There would be no room for surprise, innovation, or the emergence of new structures. Quantum randomness breaks this fixed script. It introduces novelty, unpredictability, creativity into the cosmos. If the future is not predetermined, then the very concept of destiny loses its meaning. There is no cosmic plan written in advance, no fate inscribed in the stars, no path laid out that we should follow. Quantum indeterminacy frees us from the idea that everything is decided beforehand. It tells us that the universe is constantly inventing itself and that we participate in this invention. It doesn't mean that everything is possible at every moment, the laws of physics still apply. Quantum probabilities are rigorously defined, but within the framework of these laws, there remains a small margin of maneuver, a space of indeterminacy where the future can take different forms. Quantum randomness is not a flaw of the universe. It is perhaps its most precious characteristic. It is what prevents the universe from being a boring deterministic machine. It is what allows creativity, novelty, the emergence of the unexpected. Quantum randomness breaks this script. It introduces freedom into the cosmos, not human freedom. That is a more complex question, but a more fundamental freedom. The freedom the universe has to surprise itself. This quantum randomness reveals something extraordinary in our universe. The future is never written in advance.